You walk into a packed classroom after lunch, and within 20 minutes something feels off. Heads get heavy. Focus slips. The air feels used. You can't see what changed, but you can measure it. Carbon dioxide. We exhale it constantly, and indoors it builds up as a near-perfect proxy for how stale the air has become. So here's the engineering question hiding in that drowsy room: how much fresh air must we push through to keep it healthy? Today we size it from scratch. No rules of thumb, no black box. Every ventilation problem is the same idea underneath: conservation of mass, applied to one gas. Picture the room as a box. 3 things happen to carbon dioxide. Fresh air carries a little in the outdoor background, about 400 parts per million. People generate it inside, that's our source G. And the exhaust carries it out. We make one honest assumption: the air is well mixed, so the concentration leaving equals the concentration in the room. Real rooms aren't perfectly mixed, but for sizing ventilation it's the standard, defensible starting point. Now we just write the balance. Accumulation in the room equals what comes in, minus what goes out, plus what's generated. In symbols, volume times the rate of change of concentration equals Q times the outdoor concentration, minus Q times the indoor concentration, plus the generation rate G. Now, steady state means we've reached a balance. The concentration has stopped changing, so dC dt is 0. That single condition collapses everything. Rearranged, it says something beautifully simple. The carbon dioxide generated by the people must exactly equal the ventilation rate, times the concentration rise we allow. Generation in, generation flushed out. That's the equation we'll solve. Let's put numbers in. 30 people, each generating about 0.005 of a liter of carbon dioxide per second, roughly a third of a liter a minute at light, seated activity. I'll be honest, that per person figure isn't a universal constant, it climbs with how hard people work, so we state it openly rather than hide it. Total generation, not 0.15 liters per second. The concentration rise we allow is 1000 minus 400, 600 parts per million. Divide, and the required fresh airflow is 250 liters per second. That's 900 cubic meters an hour. And here's the reassuring part. Divide by 30 people and you get 8.3 liters per second each, sitting right on top of the ASHRAE standard for classrooms. Our from-scratch answer agrees with the code. The physics and the handbook meet. Engineers rarely talk in liters per second on site. They talk in air changes per hour, ACH. It's an intuitive unit: how many times, in 1 hour, do we replace the room's entire volume of air? Just divide the flow by the room volume. 900 cubic meters an hour, over 220.5, gives 4.08. So our classroom needs about 4 air changes every hour, 1 complete refresh roughly every 15 minutes. Hold on to that number. It also tells us how fast the room can recover. One subtlety the steady-state equation hides: the room doesn't jump to 1000 ppm. It climbs there. Start with fresh air at 400, fill the room with 30 people, and the concentration rises fast at first, then slowly levels off, approaching but never quite snapping to that 1000 ppm ceiling. The shape is exponential, and its character is set by one number, the time constant, 1 over the ACH, about 15 minutes here. After 1 time constant you're most of the way there, after 3, essentially settled. So when we design for 1000 ppm, we're really designing the ceiling the room approaches during a full class. Now flip it around. What happens when class ends? Class is over, the room's at 1200 ppm, everyone leaves. Now the source switches off, G is 0, and the same balance becomes a pure decay. The solution is a falling exponential. The concentration relaxes from its starting value back down toward the outdoor 400, at a rate set by that same ACH. Suppose we want the room back under 600 ppm before the next group arrives. Set up the ratio, 600 minus 400, over 1200 minus 400, that's 1/4. Take the natural log, divide by the ACH, and the room clears in 20.4 minutes. Notice we never needed a new equation. The same conservation law, with the source turned off, answered a completely different question. Not how much air, but how long. Here's why this one equation is worth owning. Swap the classroom for an operating room. The method doesn't change at all, but the target does. We're no longer chasing comfort, we're flushing airborne contaminants and protecting a sterile field. So the required air changes jump. A general hospital ward runs around 6 per hour, but an operating room is designed for roughly 20. Run the same numbers and that theater moves over 4,000 cubic meters of air every hour, and can clear 99% of a contaminant in under 14 minutes. Classroom, ward, operating room, one conservation law sizes them all. Only the number you're willing to tolerate changes. So let's tie it together. 1 mass balance, 3 answers. At steady state it tells you how much fresh air a room needs. For our classroom, 250 liters per second, about 4 air changes an hour. Turn off the source and the same law tells you how long the room takes to clear, 20 minutes. And switch the room type, and it scales from a classroom to a hospital theater without changing a single step of the method. That's the whole point of building physics from scratch, not memorizing ACH tables, but owning the one equation they all come from. Next time, we'll move from the air you breathe to the sound you hear, and design a room's reverberation. See you there.